We're going to solve an exercise that is a dry gas well connected to a flow line and producing to a separator. So here we have reservoir pressure someplace in the formation, flowing bottom hole pressure. Then we have here the Christmas tree. At this location we have a wellhead pressure. Then we have our choke that in this case we're going to consider is fully open, and then finally we have a separator where we produce gas, and we're going to assume only gas. So we want to find out the equilibrium rate of this system, and the first approximation we're going to make is that neglecting the flow line. That means that wellhead pressure is going to be equal to P at the separator. Okay, and fully open choke. So what we're going to do is we're going to select an equilibrium point. Okay, in this case can be the bottom hole. And we want to find the curves at that point. Okay, so we want to have the available pressure, which is going to be calculated co-current from the reservoir all the way to the bottom hole, which is going to be our IPR. This is our IPR. And then we are going to calculate from the wellhead all the way down to the bottom hole, and this is going to be our TPR. And this intersection is going to give us the equilibrium rate of the system when I put them together. So for the inflow, we're going to use the back pressure equation. The low pressure back pressure equation with an exponent we're going to see now is going to be different than 1, so we're going to have some high velocity flow. And for the tubing, we're going to use this equation that we covered in the last lecture. The tubing dry gas equation to the power of 0.5. Okay, so we have here all the data. We have C, N, CT, and S. And you will see these values were calculated using the equation that we discussed in the previous lecture. Okay, and this is the details of the calculation of the CT and S. Okay, so we are assuming a tubing with is a vertical tubing. Where is the angle? It's not here, but it's the length and the height difference, they are the same. So this means that it's a vertical tubing. Has a size of 0.157 meters. I think this is 6 inch. Gas specific gravity, you are assuming here some inlet and outlet temperature. Maybe we measure in the field. Inlet pressure, we are assuming reservoir pressure, and outlet pressure, we are assuming separator pressure. Then with these two, we calculate the average temperature and the average pressure. We calculate the average compressibility factor at those temperatures and average temperature and pressure. And then with that, we calculate the S and the CT, okay, the fluid flow constant. And let's see what's behind Alt F11. So we have here one module called calculation of flow constant, in which we have CF, and we have that equation that we have covered before, where the C is proportional to the 5, and it has all of these constants. Okay, and the S, we have also the definition of S here. That is the height difference between the two ends points of the pipe. So you see here, to calculate that, we have done some approximation, but actually the pressures might be very different. Okay, wellhead pressure is 40, that's right, but bottom hole pressure will depend on what is the intersection point. But let's keep it like that for now. Okay, so to do the calculation, we have to draw the two curves. Okay, we have to calculate the available and the required. So let's start first with the available. And the available is, we're going to say, well, bottom hole pressure is, we know, can fluctuate. The maximum, the intersection has to be between reservoir pressure and maybe between 0, okay, which we know is not the case. It should be 40, but let's take it all the way to 0. okay, because we know that the IPR exists within that range. So I'm going to put some numbers here, okay, all the way to 0, and then to calculate the IPR, we have this back pressure equation has been programmed. You go here to the module flow equations. We have the IPR to calculate the QG. That's the one we have. Okay, we have reservoir pressure, we have flowing bottom hole pressure, and we have C and N. Okay, so let's use that. Here is IPR QG, and C is here. Block it. N is here, and PR is this first one. I block it, and PWF is this one. Okay, initially at 0, when PWF is equal to reservoir pressure, the rate is 0, but then it increases all the way to 3 million. Again, if we come here and see what does it show? It shows a behavior which is typical for dry gas, in which we have kind of a nonlinear behavior. Okay, it curves at high rates. Okay, now we want to, after we have that curve, we want to move from the wellhead. We have that pressure and we want to calculate that pressure. We have the rates, okay, because we have calculated, we know that the intersection has to be within this range of rates. Okay, if there is an intersection with this curve, it should be here. So I'm going to use the same rates that I have here, but now I want to move from the separator or from the wellhead all the way down to the bottom hole. Okay, so for that I should use the equation is this one, and I have to clear out from here the PWF. So then I have that equation is essentially PWH plus QG over CT squared, and the square root of sorry, this times e to the s okay, I think it's like that if I didn't make a mistake. P Okay, so you see that the pressure at the bottom hole has two components. So one is the pressure at the wellhead scaled by a let me see if I think it's correct. Okay, so it's the pressure at the wellhead scaled by some, that is, this is the hydrostatic head plus this is the friction term. Okay, plus kind of the friction. So let's see, that equation we have here is a tubing P1. Okay, here we're defining in all the convention for all of these functions, we are defining that one, if we have, let's say we have our tubing, okay, and we can define a point 1 and a point 2 by the direction of the flow. Okay, if the flow is always going from 1 to 2. So in this case, we're saying that this is P wellhead and this is PWF. So we have P2 and we want to find P1. So the equation we want to use is P1, but let's just verify that we have tubing P1. We have this exponential. Okay, I should have, of course, I should be the square root applies, yeah, because in this case it's outside. Okay, and then we have the P2 squared, which is the wellhead pressure plus the QG divided by 2 and divided by CT. Okay, so let's use that equation. Tubing P1. Tubing P1 is using the CT, which is here, the S, this one, and then the P2 is going to be separator pressure, and the QG is going to be that Q. Okay, you see initially when I have no flow, the pressure, I will have a 3 bar greater than the wellhead pressure. That means that's the hydrostatic column of gas. It accounts to 3 bar in this length, which is 2.8 kilometers. And then we drag it down, and then we see, well, actually we have here all the way when we have this very high rate, we have 90 bar. Okay, so let's see the intersection. We see this, when we put these two together, we're going to end up with that point, which is close to, I think this is close to 2.8. Okay, to find exactly the value of the intersection, I might use the solver or the goal seek, and I want to make these two exactly the same. Okay, I want to make two exactly the same, and I think this is around 2.8 e to the 6. Okay, but if I want to find the exact value, okay, I might do something like that. I might extend, for example, this. Okay, and here I just want to guess that pressure. So the flowing bottom hole pressure here seems to be here, which is close to, let's say, 80. Okay, so that may be close to 80. And that difference should be equal to 0. Okay, so I can put here some error that this pressure minus this pressure, this should be equal to 0. Okay, and then can use here the solver, or I can use the goal seek, that I want to set this cell to be equal to 0 by changing this one, which is an input. Okay, so that's the total solution, 84 and 2.85. That's how I found my equilibrium point. Okay, 84.37 and 2.85. 2.85, and this is 84.87 bar. Okay, so that's going to be my intersection, but let's see what happens now with, now the pressure that I have is 84 and 40 at the top. So I want to see like what is the effect on my intersection on the tubing constant. Okay, so now let's see, I have now the inlet pressure is not 305, but is 84. Okay, so you see the CT change from, it's almost, I think the change is very, very mild. Okay, you see that you have 441, and then when I change to is 434. Okay, and you see the S, the elevation coefficient is 302 and 310. Okay, so this change is usually very small. Okay, so what happens if, let's say I use a smaller tubing? What happens if now the tubing was, the diameter was much smaller? Okay, and here I have, if everything else remains constant, then what happens if my diameter is changing? And I'm going to say, let's use a diameter which is half the size of the previous. Okay, half the diameter, half the value of the previous. Okay, and now this will be my C. Okay, and I'm going to paste it here. Oops, what happened? Copy. Okay, and now you see, well, essentially now the intersection is at a rate much lower. Okay, you have before 2.87, and now you have an intersection which is um, close to 1.5. Okay, so this is effect of tubing size. So if the diameter is reduced, then also the CT will be reduced, and therefore the equilibrium rate will be reduced. Okay, in this case, this diameter is 0.077, okay, something like that, meters. Also, let's see at the effect of The original, was something. This point won't change, okay, because you're not changing the hydrostatic head. The diameter of the pipe can be 1 meter, can be 0.15, can be 0.077, but it will still have the same point. But the intersection before it was here, okay, but now it changed there.